I am Carlo Rovelli, and I'm going to talk about vision and science. I'm going to talk about the visionary aspect of science and argue, first of all, that vision, image have a central role in scientific discovery, and then that even more than that, there is a contiguity between vision, literally seeing, and doing science. It's sort of one the continuation of the other in some specific sense. And finally, we'll talk about perspective, perspective being a core aspect of vision and also science.
So, good evening and welcome to the fifth of this 2019 Darwin College lecture series on the theme of vision. As you know, last week we were concerned with technology and visions of the future, and this week we return effectively to the present, to physics, and almost in some sense to philosophy. At school you learn about the giants of 17th century physics, about Galileo Galilei and Isaac Newton. Galileo's principle of inertia, his development of telescopes, and discovery that the planets orbit the sun, not the Earth. And then later, of course, Newton built on his ideas. So, we learn about gravity at school. It's an attractive force between two masses. And, the legend is that it's Newton and a falling apple. I wonder what happened if Newton had eaten that apple or if it had knocked him out. Might our vision of the universe now be different? Would our view of reality today be what it is now? But, since the 17th century, physics has undergone immense advances. General relativity, quantum mechanics, string theory, and so on and so on and so on. In terms of visualization, it's much easier to imagine a falling atom than quantum mechanics. Well, we think about Schrödinger's cat. Is the grin there or not? But now it seems that even time itself may not be fundamental. How can that be? Past, present, future, that's the way we look at things. Time flows like this. Maybe that's not the case. Now, being able to visualize complex, abstract concepts really, really helps. But I sometimes wonder whether needing to visualize them in some way might limit understanding. Now, I said physics. So our lecturer this evening, a theoretical physicist at the University of Aix-Marseille, whose research includes quantum gravity and the meaning of time. He's the author of 2 books, 7 Brief Lessons on Physics, and The Order of Time. Please welcome Professor Carlo Rovelli, who will speak, as you can see, on the visionary aspect of science, scientific discovery, vision, and perspective. Carlo.
Thank you very much. Very many. Thank you for being here, so numerous. Thank you, Mary, for this introduction. I'm going to talk exactly about the topic that you raised. I'm going to say the opposite of what you said. Just the topic is vision and science. In fact, when I received the invitation for Darwin College to talk in this series, which is dedicated to vision, the first reaction was, I'm a theoretical physicist, I know nothing about vision, about our eyes work. What am I going to do? Could I talk anything meaningful about vision? And the second reaction immediately was, yes, I always wanted to talk about vision and science and trying to articulate ideas that I have about vision and science. And this is a wonderful opportunity for doing that. And so this is a result. What I'm going to do is talk about scientific discovery, vision, and perspective, and do 3 things. The main one, which will take most of the time, is to argue against what Mary just said, namely that I believe that vision, in the simplest meaning of vision, picture, images, things that we view, has a central role in modern science and in particular in modern theoretical physics as it has had in science always. A lot of science is visual in a sense that I will try to articulate, somehow against a reading of science. I mean, I should be careful. Karl Popper was here talking in one of the first lectures. So I don't want to challenge big names. But the Pink Floyd played here also, so I'm told. So I think that in the usual reconstruction of the scientific methodology that we get from philosophy of science or from teaching of science, vision is underplayed. And I want to argue for that. And the way I will argue for that is using the, the simplest and more silly line of arguments, a little bit middle-aged perhaps, which is just giving a lot of examples. The philosopher in the audience may want something more deep, but I will just use that. I will take you through a number of many examples and try to show you what is the point of vision into science and argue what is completely central. And then in the last part, at the end of the talk, I will draw some I hope deeper conclusions from that. I will make 2 points. I'll just put the titles here. We'll get there at the end. One is that, in fact, I think that there is a contiguity between vision and science, which is strong, which helps us understanding what science actually is, what we do when we do science. And the second, I want to talk about perspective. Perspective is a key aspect of vision. We always see things from a perspective. And I want to argue it's a key aspect of science, the methodology of science and what science does, but also, according to contemporary physics, is a key aspect of the structure of the grammar of reality itself. I'll get that to the end. So let me start from somehow making the point that Mary was saying a moment ago. Modern science is constantly blamed, if I may, to be very mathematical, cannot be visualized. What is a quark, a Higgs particle, the 10-dimensional something or whatever, has modern science, and in particular modern physics, abandoned visual intuition. By the way, it's a question that I've been asked by journalists constantly. Every journalist who asks me, well, what you guys are doing is completely non-comprehensible and non-visual. This is a cartoon of it. There's all sorts of story, non-commutative algebras, higher dimensions, virtual particle, funny equations, and the theoretical physicist is somebody who says, yes, of course, this is an explanation along line of equation, and the man of the public say, oh, yeah. Okay. So I want to argue that this is not the case in some sense, and that, as I said, visual intuition plays a central role in science. And let me start from the quintessential, the iconical modern physics guy, who is Albert Einstein, in fact, and from the theory that, when it came out, was presented by journalists as a theory that could only be understood by 12 people around, which is general relativity. General relativity, it's about curved spacetimes. There's been a lot of talking recently about special relativity because a sequence of spectacular confirmations, black hole and gravitational waves, was in all the front pages of newspaper. Gravitational waves is space-time waving. There's just a wave of space-time. Imagine, that's a picture of a waving of space-time. Imagine being immersed in space like in a big jelly. Einstein used the image of a jellyfish. Space is like a jellyfish. We're immersed inside it. And you can shake it, and there's this vibration that moves through, and that's a gravitational wave. And what a mass does is curve space-time. What does it mean, curve space-time? If you put a heavy thing on a rubber sheet, you probably always have encountered this image here. it stretches. So there's an elongation in the direction radial to the mass. Now, the point I want to make is that these pictures, the waves of space-time, the curving of space around the mass, are not a after-the-fact attempt to popularize complicated equations. It's the other way around. This is the original intuition that Einstein had, from which he developed the theory. That's the picture he had the kind of picture he had in his mind, and he looked for mathematics for transforming this picture in something predictive related to data and so on and so forth. Let me be clear. I'm not saying, obviously, that the theory can be reduced to the pictures, obviously. I mean, there's a huge amount of stuff into science, which is data collecting, which is mathematics, calculation, checking, testing, et cetera, et cetera, et cetera. All that big part. But I want to say that all this messy part, it's motivated in the mind of the people, of the persons who start the theory from a picture, an image. And trying to make sense of this image and see whether this image is useful to better understand the world is what happens in science. Let me stay with Einstein. He got the Nobel Prize for the photons. The paper of the photons is a 1905 paper. It's a spectacularly beautiful paper. It's enormously important, not only because he understood that light is made by photons, but because it's the real paper that started quantum mechanics. So Einstein is also the source of quantum mechanics. 5 years earlier, Max Planck had written this formula here. The energy is proportional to the frequency of light with some proportionality constant, and now we call a Planck constant. And Planck had no idea what this formula meant. He says so clearly. Why the energy is proportional to the constant doesn't make any sense for a physicist. And Einstein came up with a visual understanding of that picture by saying, well, it's very that formula, which is very simple. In fact, it's beautiful. In the abstract of the paper, Einstein writes, it seems to me that some phenomena related to light can be better understood if instead of thinking of light as a wave, like Maxwell told us to do, we think of light as made by little packets, little grains of light coming to you, sort of raining over you. And the size, the energy of the packets, how big they are, depend on the frequency. The frequency is the color. So a more reddish light, as a smaller frequency, has smaller packets, smaller grain. A more bluish light as bigger grains. So the color of the light is the size of little quanta, as we say today, the photons. Good. So there's nothing more visual than this idea that light is made of little stones. If you read the paper, the way Einstein argues for that, let me try to render it in simple words. And again, the point I want to make is how visual is it. Think about that. He uses the photoelectric effect. In fact, the paper, big chunk of the paper is about the photoelectric effect. And the photoelectric effect is light falling on a metal and electrons being kicked out. But there's something strange. There was something strange on the photoelectric effect that electrons are kicked out not when there's a lot of light, but when light has high frequency. Which doesn't make any sense. Because a lot of light uses a lot of energy, will kick up more electrons. No. You need high frequency. So here is the explanation. Think about a hailstorm. Okay? Big hailstorm. And suppose you have your car parked outside, and you worry because the hail is going to hit on your car and make bumps on it. What makes you worry? The total amount of hail, of ice coming down? No, that doesn't matter. It's the size of the stones, of the pellets of ice, right? So a little amount of ice falling down, but in big chunks, is going to hit your car and make a big bump. A huge amount of hail, small stones, is not going to do anything. So what matters is not the total amount, total energy, but the size of the things. Now, the photoelectric effect what you see in the laboratory is that the electron is not kicked out by the total amount of light, but by the frequency. So Einstein said, aha, the frequency, that's what this formula means. The frequency is the size of the stones. Because big frequency, big stones, photoelectric effect, like the big stones of hail make a bump into your car. This is a simple story behind the paper that got Einstein a Nobel Prize, right? It's completely visual. You can make it completely in picture. And every physicist loves Einstein. So let me make one more step with Einstein, another of the super great Einstein discoveries. I think that one will still make him one of the greatest physicists, even if he hadn't done anything else. The Brownian motion. He had, in 1905, he had another paper showing, it's the paper that shows that atoms are real, that matter is made by molecules. And the way our, atoms is a very old idea. It goes back to antiquity, Democritus, and the chemists used atoms all through the modern time, but the physicists were never convinced by atoms. Many physicists at the end of the 19th century still didn't believe in atoms and molecules. And Einstein came out with a paper that convinced everybody and had a very strong argument and indeed computed the size of the atoms. And this is the celebrated Brownian motion paper by Einstein. And it's very simple. Brownian motion is the motion of particles that you observe, a teeny grain of dust in air, move in a funny jumping way. Einstein observed, well, why they move in this funny dancing way? Because they're hit by the molecules. And if the ratio between the size of the grain of dust and the molecules is different, they're going to move differently. So if they're bigger, the grain of dust is going to move less. If they're smaller, going to move more. So from the amount of motion, I can reconstruct the size of the molecules. He does a calculation. The calculation is not easy. You need to be Einstein to invent and do all the statistics of that. But the idea is simple. It is just completely visual. You see the molecules bouncing around these things. It's just completely visual. So this is how Einstein was visual in these things. Second example. I'm going to do many, and I hope to give you, and then with many I will also bring different aspects to the visual way in which science works. All of modern physics is modern fundamental physics, elementary particle physics, relativity, builds on the notion of field. Fields are often presented as something hard to visualize. Sometimes you read, well, Feynman wrote, I can't visualize the electromagnetic field. Feynman loved to say this kind of thing. Nobody understands quantum mechanics, nobody understands it. Because he was American, he liked to say, you couldn't understand. But the field, the notion of field was invented by Faraday and was formalized by Maxwell, but it's really Faraday intuition. If you go through his book, beautiful book, and you look where fields appear, here's what fields appear, right? It's just a picture. Before anything else, fields are a picture. This is a magnet, and he thinks that the reason magnet attract stuff, a piece of metal, blink, is attracted by metal, is because there are these lines that go around it, fill out space. Now we call it Faraday lines, and that's what the field is. What Maxwell did is put a vector, a little vector in any point here, and that's how the mathematical notion of fields come out. But the notion of field was completely visual to start with, and it's completely clear if you read the Faraday book. Let me leave physics and go to a completely different subject. I don't want to talk only about physics, which is biology. The two, perhaps, greatest central discoveries of biology, one could say, are the DNA in a century before Darwin. The DNA, discovery of DNA, where is the information, where is stored the information that goes from the parent to the children, is started out in this paper by these two guys here, but I want to put Rosalind Franklin there because she's probably more responsible for it, and she's still under recognized for it. But Crick and Watson When they came out with a paper, this is a paper, and the key point of the paper is just this picture here, right? There is this structure, which are the two strands, which go in a helicoidal way, but the point is not the helix, the important point. The point is the two strands with this things in between, which alternate different kind of chemicals, and this gives the codes, and the code is where the information is stored. And the first thing they did, when they got to this idea, they built a model. Here's a model they built, and they went to the head of the lab, showing the model, and they immediately started presenting the image of that. Once again, it's a picture at the beginning of the story. And Darwin, that's the right place to talk about Darwin. I think this page of his notebook is very well known. It's a famous page of Darwin notebook. If you read the book by Darwin, The Origin of Species, it's a marvelous book with a long, extremely well argumented argument for evolution, natural selection, and so on and so forth. With a lot of observation, enormous amount of observation, subtle thinking, and built the argument. It's beautiful and complex, and there's an enormous amount of his own observation behind that, and so on and so forth. But it all came out from a flash that came to his mind when he was still young and still going around in his trip around the world. I hope I'm not saying something wrong. Correct me if I'm saying something wrong about when he actually wrote that. But in his notebook, this is the moment in which he got the idea. And the idea is nothing simpler. There's this incredible variety of living beings, animals and plants, which resemble one another a lot, but also so diversified. Where does it come from? How is it possible that there is this incredible complexity, but also all these similarities? And yeah, it's like a branching thing. It's the tree of life. It was one species that branched off in three, and then each branched, and that's the origin of the complexity. And then slowly behind that, it comes the two key ideas on which the book is based: the variation, the branching, and the selection, the choice between that. Once again, at the origin is an image that has been building in his mind through all the rest. And once again, it's not that the theory of natural selection is reduced to this image, but it's based on that image. Now let me go to the hard part, because you could say, okay, so these are the easy examples, but what about the hard stuff? Quantum mechanics. Nobody visualized quantum mechanics. Good. So let me go to quantum mechanics. Quantum mechanics, I hope there are physicists here who can disagree with what I say and be surprised what I say. It was invented in 1925 by Werner Heisenberg, and within the year almost completed in a series of papers by him, Bohr, and Jordan. And quantum mechanics is definitely harder to visualize to start with. But if you try to reconstruct what happened in Heisenberg's mind when he got there, there's a beautiful reconstruction in Copenhagen, the play, in which Heisenberg himself tells a story about the idea coming to his mind, talking with Niels Bohr. And the way he tells the story is the following, is marvelous, I think. He's alone in the park in the night outside what is today the Niels Bohr Institute in Copenhagen, the institute where Niels Bohr at the time was studying, and Heisenberg was 24, something like that, was studying there. He goes out, mumbling about all the problems of the atoms, and it doesn't work, classical mechanics doesn't work, the old quantum theory doesn't make sense, what is going on there? And he sees a man. You see the man there? But it's very dark. And it's always everything black except for some lamps. And he sees a man walking, but he doesn't really see the man walking. He sees the man disappearing in the dark, and then reappearing there, and then disappearing in the dark, and then reappearing there, and so on and so forth. And then you think, well, of course, the man is not disappearing and reappearing, because a man is, is a big, heavy thing, which I know is walking through. I know it's in between when I don't see him, it's there. And then he has a flash of light. Wait a moment. That's for a man who's big and heavy. But what about an electron? How do I know? If I see the electron here, I see the electron there, what do I know about the fact that in between the electron is somewhere? And there he has an idea, forget the in between. Maybe the electron is the sequence of snaps, which appears when the electron interacts with something other. It's the name we give to the sequence of interactions that something has with something else. That's the founding intuition of quantum mechanics, and that's what non-commutative algebra and everything is about. Now, that's not easy, and in fact, the physicists were not happy with that, to the point that 1 year later, another scientist, Austrian, doesn't want to come in. Here he is, Erwin Schrödinger, gave a different story, which turned out to be mathematically equivalent, but it was formulated a different way. And the story was about a wave, psi, the famous wave function of quantum mechanics, and that's the Schrödinger equation, is how this wave evolves in time. I think this is a bad way of viewing quantum mechanics, but it's more visual, because you can picture this wave. For instance, if you solve this equation for an atom, the simplest atom, hydrogen, these are the possible solution, and these are the shapes the wave can be around it. It's like little clouds around it that solve this equation and have these little shapes here. So it's visual. So everybody says, oh, now I understand quantum mechanics because there's a picture attached to it. And still today, there are a lot of people who take this picture, this wavy picture of quantum mechanics, as the fundamental aspect of it, especially a philosopher in a little village outside here, how it's called, Oxford. There's a bunch of people who interpret quantum mechanics as the story of the wave, instead of the story of the discrete aspect of reality, which is Heisenberg's story. But you see, even here, where clarity is not yet there, because physicists don't agree a lot, philosophers don't agree about how to think about quantum mechanics, the real debate is how I visualize it. That's what is really the debate upon, in my opinion. Let me go to, so far has been very well established physics. Let me go to the boundaries of our knowledge, where it's just speculations. And you all know this guy. Stephen Hawking, unfortunately left us, early had a lot of ideas, wonderful. We don't know if they're right, if they're wrong, many of them. But let me mention one of his beautiful ideas. He wrote a book about that, about the origin of time. The universe started expanding. What was happened before? Nothing, because there is no time before, right? He has a famous book about that, and it's one of his beautiful ideas, is in the context of a formulation of quantum gravity, which is called Euclidean quantum gravity. But the idea is a picture. Here's a picture. The universe is expanding, so time goes up. You have this expanding universe. If you go back, you don't go to a point from which a Big Bang is not a point, an explosion from which what happened, because you can think of rounded up. There's no special point where is the beginning of the story. Now, to do that, you have to change the mathematics to go to something which is Euclidean. It's a long story. But once you digest the mathematics, or even before digesting the mathematics, the idea is that perhaps the beginning of time is like the northern point of the Earth, the North Pole. Is that a special point? No, you go there, it's not a special point at all. Many points. It's just how you... In fact, there is a magnetic North Pole, there is a geographical North Pole, and all sorts of North Poles. There's nothing special happening there. So maybe the beginning of time, there's nothing happening there. Once again, the point I'm making is that this picture is not a simplified popularization of a complicated mathematics of Stephen. It's the other way around. The complicated mathematics, it's a way he tries to make this visual intuition working to actually describe the world qualitatively and quantitatively. It's not that the picture itself is sufficient, of course. If you don't do the rest, you're not doing science. But you don't do the science without doing the picture. This is Roger Penrose, great friend of Hawking and one of the greatest mathematicians and theoretical physicist. One of the great contributions he has given to relativity and theoretical physics, a tool that is used by relatives all the time, is what is called a Penrose diagram, or the Carter-Penrose diagram. It's a picture like that represent the history of the universe with a few simple rules in a small diagram. This is a black hole, this is a star collapsing, this is the horizon of the black hole is a triangle here, and that hypothesis that the black hole shrinks, disappears, and then later there's no black hole at all. Physicists use that all the time. If you come to my research group in Marseille, picture like that on the blackboard all the time. It's all about picture before being about equations. And I'll come back to this picture. I think this picture is wrong, by the way. Not the Carter-Penrose diagrams are wrong. That's a fantastic tool, they're right. But that's a wrong description of the black hole. I'll come back. Good. So before coming back to that, let me not overplay this. I don't want to say that every theory, every great idea in science is visual. There are definitely exceptions. Here is an exception, Dirac. Dirac is from a different galaxy. I mean, the way he thinks, he's a poet, something, he's a genius, he's something. He doesn't think visually. He thinks in terms of equation. And in fact, this is the Dirac equation. Today is the equation that describes how an electron moves, a quark moves. So it's a fundamental equation in the physics, a piece of standard model, how the fermions move. And I don't think there is a decent picture behind this equation. I don't think Dirac had a picture in the sense we usually say a visual image. Maybe he had some structure in his mind, but I don't see them. I cannot see them. So definitely there are exceptions. But let me talk about this exception. In a sense, you can distinguish physicists. There are those like Dirac, who think in terms of equation, and those like Roger Penrose, who think in terms of images. And if I may tell a story where I was present and I could witness, I worked in the United States before coming back to Europe, and I worked in Pittsburgh, and I worked in the group of Ted Newman. Ted Newman is one of the great relativists. This is Ted, and Ted Newman was a good friend with Roger Penrose, and they've done a lot of physics together, the Newman-Penrose formalism, a lot of stuff. And they've worked together all through their life. And Roger was coming to Pittsburgh and working with Ted, which is an office next to me. And this young faculty, I was the great two people. I was just patting in the office of Ted and sitting in a corner, quite a small chair, and listening to these two people talking. And it was absolutely marvelous. Because Ted is like Dirac. He's an equation guy. He's totally algebraic. And Roger is like Einstein. He's the most visual person of the world. So here was a conversation. I know I was sitting there and listening. Roger would say, okay, Ted, look, I think I see it. Imagine, it's easy. There's a 7-dimensional space with a foliation that wraps around in 2 dimensions in 7. And of course, here, 4 other complex dimension. And slowly he would build this picture. This is a Robinson congruence is one of the things that Roger loved. In fact, he keeps. And Ted, I remember, was listening, with blank eyes. So what the hell are you talking about? And then, Roger was insisting, and Ted was asking questions and being confused. After a while, and that's the point, Ted was understanding. I said, yeah. I think I see what you see. And then he would stand up and say, is that what you mean? And go to the blackboard. And Roger would look at this blackboard with just blank eyes. What are you talking about? And that was the idea, look, there is this blah, 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 blah. And Roger was, yeah. And so this was working on. And they did fantastic physics together. So what's the point? It's not necessarily visual. Ted has never been visual. It's very much like Dirac. But there is a translation between the two pictures. This is not really the right equation for that because I didn't find it. But there's an equation, a set of equations that describe that, and there's a picture that describes that. So there's always a translation between a set of equations and some imaginary. And in the mind of the scientist, very often there are different ways of saying the same thing. And I've brought myself into this story, so allow me to, in the middle of all these great names, to put also your humble speaker here. He's your humble speaker, a younger chap. My tentative contribution to science is in quantum gravity and about the granular aspect, not of light, not of matter, but of space itself, space being grains. And the grains are attached to one another. They know who is next to whom. They're not sitting in space. They build up space themselves. This is the core of loop quantum gravity, the theory in which I've worked most of my life. It's a picture. So all my life, I've tried to make this picture into equations, find the right equation describing this picture, and then trying to see whether these equations are good or not to describe the world. Can we test them experimentally and so on and so forth. And the first thing I did when Liz Molling and I came out with this picture is try to build a model. This is me as a young man building an actual three-dimensional model of this thing which was in our picture. And today, what we're working on with my collaborators, with a group, with other groups in the world, is one of the problems left over by Stephen Hawking. What happened when the black hole shrinks, evaporates, becomes small? What happened next? Okay? And the intuition I've developed with others, Francesca Vidotto is sitting there, is one of my collaborators, is that the future of black holes is that it bounces back. It's a few years that we're trying to make this into a credible story, compare it with observation, make the right mathematics of this, connect to the discrete structure of space-time, which happens in the bouncing point. And one of the tools we use for doing that is Penrose diagrams. This is a diagram of a black hole becoming nothing. This is a black hole of a black hole, the diagram of a black hole bouncing into a white hole. Once again, the discussion is this picture right or is this picture right? Which picture is the right one? And all the mathematics and everything else, it's about pictures. So scientific intuition and scientific discoveries are, I wouldn't say always, almost always, I would say intensely visual. And let me even step back for a moment, go back in time to say that this has always been the case, and this will lead me to the next observations. Well, Newton is probably the greatest scientist of all the times. He has done all sorts of things. What's the main thing he has done? Universal gravitation. What is universal gravitation? Is a discovery that falling things, the reason this falls, and orbiting things, the moon going around the Earth, the planets going around the sun, follow the same logic. It's the same story, same equations, the same rules. How did he get to that? Well, let's just flip through the Newton text. Here's a picture in one of his books. It's very simple. This is the Earth. Suppose you're on a mountain and you throw something. It falls down. Well, no. You throw it longer, it falls here. You throw it stronger, it falls here. You throw it even stronger, whoop, it falls here. You throw it even stronger, it falls, and get back to your head. You put down, it goes through, and it keeps going around. So falling and orbiting is the same thing, and it's immediately visual from this picture here. I am strongly convinced that before writing the Principia, before doing his little moon calculation and all the thing, that's a picture he had in mind. In fact, he might have got this picture from Galileo even. This is it's an image, is a visual image that justifies. Mary, you mentioned Galileo. This is Galileo confirming, finding elements for confirming the Copernican revolution. The strongest, one of the strongest elements that Galileo finds to confirm the Copernican revolution is the moon of Jupiter. Because in Copernicus there's an anomaly. And everything goes around the sun, picture, and the Earth has its own moon. So the Earth is something anomalous. But then Galileo sees with a telescope images. He found a new way of looking images, and see the moon of Jupiter. This is Jupiter, and this is the four moons. Jove is Jupiter in Italian. Quattro stelle is 4 moons, 4 stars. And he sees Jupiter moving along the fixed star, but this 4 star moving with it. It's a completely visual story that brings the strongest argument in favor of the scientific revolution. And let me get to the scientific revolution. The scientific revolution. What is a scientific revolution, right? There's this picture here. Once again, it's like Darwin. It's a huge book, the De Revolutionibus by Copernicus, from where this picture is. This is from his book. It's a huge book with a table of trigonometry, with all the geometry, with all the data, with all the prediction, and blah, 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 blah. But the point is very simple. Instead of the picture Earth, planets going around, there's a new picture. Sun, I mean, the picture you know very well. The sun and the planets going around, and the Earth with the little moon here. Is the anomaly that Galileo corrected. There is a greatest scientific revolution, perhaps, or an equally great scientific revolution, which happened 20 centuries earlier in Greece by a scientist called Anaximander of Miletus, of which I'm particularly attracted. I wrote a book on Anaximander of Miletus, because I think he's one of the greatest scientists ever living. And in fact, there's a guy who agrees with me, which is Karl Popper, who was here. Anaximander is the one who understood that the world is like that and not like that. Namely, the sky is not just above our head, like everybody thought for centuries of previous civilization, on all the other civilization, but the sky is all around us. So the Earth is not what's behind, but it's like a stone that floats into space, right? It's a major revolution. It's a cosmological revolution. It's also perhaps the first time humanity changed radically the picture of the world. And once again, it can be presented in a picture like this. But this also starts telling us what are these pictures, because I want to now argue a little bit what I've been presenting examples of exactly. Think what is going on from here to here? Well, this is just like this seeing from a distance, right? Imagine you're here, you're looking at the Earth, and now you move out. I move back in space, and I see the Earth, all of it. So I'm changing my perspective. I'm seeing it from a larger perspective. Anaximander himself is known for a number of other great steps, one of which he's credited in antiquity as the guy who has invented the geographical maps, which seems silly to us, but nobody used geographical maps for millennia. Nobody thought about making a picture of the land for millennia. If you were a traveler, you would get stories from your fellow travelers. You go there are mountains, and you pass, there's a city, you go there's a lake, but nobody made a picture of that. And Anaximander is known for having drawn this picture of the Earth as a whole, from which the next maps from Hecateo, from the others, are known to be derived. It's something like that. We don't have it, of course. The reconstruction is something like that. There's Greece in the middle, of course. Everybody puts themselves in the middle, wherever they are. Asia, Africa, Libya, whatever, Europe, and the ocean around. The antiquity, they thought everything is the ocean around. So this is a map. What's a map? What is a map? It's Earth seen from a bird flying very, very high. Okay? So once again, it's the same story as here. You look at something from a different point. You change perspective. And if I'm not going to do that, but if I go back to all the pictures that I showed before, all of them, or perhaps almost all of them, can be thought of viewing from a different perspective. From more far away or from more close away, the molecules, it's always viewing from a different point of view. So the core of what is happening in science can be said just that, change perspective. Not change perspective arbitrarily, find a better perspective, which is hard, of course, but find a better perspective. And once you find a better perspective, you are on business. And let me just add this because this is too beautiful. 3 centuries after Anaximander, Greece, Alexandria, Alexandrine science, the great development of ancient astronomy. This is the moment in which humanity understood that the moon is big, the sun is much bigger than the earth, the distances of the earth. So we started to make sense of what's around us. It was the first measure of the size of the earth. Everybody at this point knew that the earth is round. One of the main players in that was Aristarchus. Aristarchus is the one who measured the distance of the moon correctly. And to measure the distance of the moon, you need to know how big is the moon. And the idea to know how big is the moon is to use an eclipses, a lunar eclipses, because you see the moon going to the shadow of the earth. And the earth has a shadow, so you know roughly what is the size of the shadow, and you compare the moon going through, so you know the size of the earth. But there's a difficulty. The shadow of the earth is not a cylinder. So the shadow of the earth is not the size of the earth. This is smaller. The diameter of this shadow here, the sun is down there, right? It's big, the sun is very far away. So how do you figure out the shrinking of the size of the shadow when you go down, knowing that you don't know how far is the moon? Aristarchus has the following argument. Well, this angle here is the same as this angle here, because we all know that the sun and the moon have the apparent angular dimension in the size, right? The solar eclipses, the moon covers exactly the sun. So we see the sun and the moon under the same angle. So this is an angle under which we see the moon. Now, the sun is very far away. Suppose, says Aristotle, that we could fly there to the tip of the shadow of the earth. This is fantastic. We're in the 3rd century before the Common Era. 3rd century is before Jesus Christ, right? Before the Roman Empire, before all that. And these are people who are thinking correctly and doing wonderful scientific thinking by thinking, if I was at the tip of the shadow of the earth, very, very far away, more far distant than the earth, I would look back. I would see what? The earth covering exactly the size, the sun, because that's what shadow, the point of the shadow is. But I know that the angles to which I see the sun, which is very far away, is the same as the moon. So this angle here is the same as angle here. You do a little bit of trigonometry, you solve this, and you find the right size of the moon, from which you find the right distance of the moon was right, was correct. And that from there, we know not only the size of the Earth, but the distance of the moon, and so on and so forth. What's the beauty of here? It's the thinking about changing of perspective. It's the thinking about how would I see, if I would change perspective. And that's core in science, I would say. Science is vision from a new perspective, and is a realization that there are different perspectives about viewing things. What's perspective? Perspective, this is a master of Italian Renaissance, Piero della Francesca, who is considered one of the first masters of perspective. This is a famous painter, and this is a reconstruction of, it's not very visible here. This is, the observer is here, and his perspective on this scene, these people are sitting. You see, even the descriptor of what perspective is nothing else than seeing this from a different perspective, same scene from a different perspective. And this is a sentence which is attributed to Piero della Francesca. There is no image without perspective. There is no vision without perspective. Vision implies that there is something seen, somebody looking from a perspective, right? Now let me start to argue. I don't have much time. A little more solidly here, with a little more content. If science is a change of perspective, science is based on the recognition that what we see is seen from a perspective, and therefore is partial. So science is rooted in the awareness of the limit of our common sense perspective. This is what allows us to say that the way we see the world is not the final picture of the world. So the world, the reality is not the way it looks like, but it still looks like something. And that's somehow the key point of the entire story. This thing is not solid. It's a lot of atoms moving. Reality is not the way it looks. But a lot of atoms moving here is something that is very visual. It looks like something, right? In that sense, science is an extension of common sense, because when we change perspective to understand something better, it's not some strange thing we do. We do all this all the time, including, I want to see what happened there, I just look at it from here because I see it better. I change perspective, right? And science is this evolving way of thinking in which you look for the best perspective, for a more effective perspective, not the best, a better perspective, or a better way of viewing something. And from here, I go to the two final points that I want to make. The first point is, I've talked about vision. I used vision for talking about science. But what is vision itself? So what it is to see. And there is a lot about vision. It's not my field, so I'm just telling you things which I read in books from others. There's a lot about vision we're learning from people who study vision, and people have been talking about that, and in particular for neuroscientists. What happens in vision? Well, there's light that gets to our eyes, of course, but then there is all this computing that happens already in the retina and then in the neural wiring, which is behind in various layers. And already in the retina, all the information that comes from the vision is reduced by looking at patterns. I'll say what I mean by patterns in a moment. It's pattern recognition. So here's the key point. Patterns are consistent structures which organize the data. What does it mean, organize the data? Comparing to the memory allows us to predict the data. So a lot of recent neuroscience about vision is telling us that vision is not information going this way from the eyes to the brain. It's a lot about information going down from the brain to the eyes. So what the brain does, it has memories, general memories about things. We know that an object remains an object. I've seen this is black. I expect it to be still black. So the brain tells the eyes, the neural structure tells down what we expect to see, and then there's a comparison between expectation and seeing. And when there is something wrong, which always is something wrong, there is something new, this is what we see. We see the discrepancies between what the brain expects on the basis of its memory and the data which are coming here. And how does brain play this game? How can it anticipate? Because it recognizes structural patterns which are regularity that allow these things to. What is science? Science, I read from, I don't know, the logical positive reconstruction of science, is a search for wider patterns than what we recognize individually. It's the search of consistent structure, organizing data, matching with what we know, which allow prediction. It's actually the same thing. When we see and when we do science, we're doing the same thing. We're getting patterns in the region of our experience in an organized way, sufficient for making predictions, and every time predictions don't match, we reorganize it. Of course, in vision, we do it on a short time scale and individually. In science, we do it on a larger time scale and culturally as a community. But that's what we're looking at, patterns organizing experience. I think that a great intellectual, which is, in my opinion, underestimated, who has this focus on truth as organization of experiences, is Bogdanov. I don't want to go into that. Alexander Bogdanov has great books he's writing. I recommend you to read it. Now, in these days, it's pretty fashionable to talk about structures, and there is a part of philosophy of science which is talking about what is called structural realism, the idea that we can be realist in the world, not about entities, but about structures. I find it, on the one hand, extremely interesting, and on the other hand, I'm not a philosopher of science, a scientist, so I'm just giving you a reaction to that. I'm puzzled by that. Interesting because the focus is on structures, and that's what definitely what these patterns that we see and we do, we care about in science are structure. Instead of entities, what are entities? I mean, we're all children of Hume. Entities are structures in data. What else they are? What I find not convincing in structural realism is this hope that the structures themselves don't change. Of course they change. It's all about changing structures, which science is about. The sun has remained the sun more than the structure we use to describe it change through ages. Of course, the sun has gone from a little yellow stuff to a huge burning thing to a bunch of nuclear reaction. We change our image of the sun. We change our perspective of the sun. We change our pictures of the sun, but the sun is always the sun. And the kind of structure we organize it changes. But, you know, let me close this more philosophy of science parenthesis. I am, and that's why I was happy to talk about vision and science here. I think that science is not just metaphorically, but even literally, an extension of vision. We are just doing in science what we do in vision. We detect patterns in the experience, stable enough to allow prediction, and we constantly test them and updating them. Why we do that? Because it's usual for survival, of course. So it's biology behind that. We've been selected to do that. I find it astonishing that this description of what the thing is the same for vision and for science. Last point, perspective. I've mentioned perspective. I used a lot of my time, so I'll go short with that. I'll just throw a few hints to you. It's something which I keep thinking about, and I'm deeply puzzled about. And I always thought that there is something deep here. Perspectives, obviously, are plural. There is the perspective of something. There are different perspectives on things. I can look at my hand from this side, from this side, from this side, different perspective. That's what perspective is. A lot of 20th century physics, it's about this plurality of perspective. And if you look at from this perspective, if you look in this way, it's surprisingly constant, this theme. Let me make 3 fast examples. One is Einstein's special relativity, the way Einstein presented it at the beginning, or the way it's usually presented in initial textbooks. It's all about a story of, you know, 2 observers, one is moving, the other is measuring, and from this perspective, from the other perspective. It's all a story about how different observers relate to one another, from the perspectival aspect of the passing of time, of the length, and so on and so forth. Second example, the best credible description we have about the universe so far, if we don't fold in the speculations like loop quantum gravity that I do or others, it's quantum field theory with generativity on curved space-time. What you learn in quantum field theory on curved space-time is that the notion of particle, the founding notion of particle physics, changes depending on the state of motion of the observer. The number of particles is different depending on how the detector of particles is accelerating, is moving. And on a curved space-time, there is no preferred acceleration. So the quintessential entity of particle physics, a particle, is a perspectival thing. Is such with respect to an observer. There are no particles here, but if I move accelerated, this is a great discovery by Unruh, there are a lot of particles here. So particles are not things. Particles are a way a special perspective allows us to organize what quantum field theory, the way a quantum field theory behaves, affect a detector. And then quantum mechanics, if you go back to Heisenberg, I started with Heisenberg, when is the electron existing in its snapping? When I see it in the interactions. So the entire discussion of quantum mechanics is what does this mean? What is a measurement in quantum mechanics? mechanics. We perfectly make sense of quantum mechanics if you have a quantum system, this S here, and an observer, which is pictured here as a medieval guy making a measurement here. So far, quantum mechanics is completely comprehensible. Quantum mechanics becomes incomprehensible when you think that this is in itself a quantum object. But it's perfectly comprehensible if this is a quantum object, it's a quantum object with respect to this observer. This is quantum mechanics in the relational interpretation of quantum mechanics, which is the one which, in my opinion, make, I wouldn't say more sense, but less nonsense. So quantum mechanics is about relative perspective that systems, physical systems, have on one another. And the best description of the world is just that. So there is a deep perspectival river into modern physics, which has always been there. One of the greatest questions of humanity, we see the star going around us, the star, the moon, everything turns around us, right? Marvelous. Humanity has been wondering for centuries why it turns. And then, you know, Copernicus and company make perfectly sense of it. It doesn't turn, it's us turning, right? That's why we see the sky turning, but it's us turning. So the phenomenon of the turning of sky is real. It's not illusory, but it's perspectival. It's a non-moving sky seen from the perspective of a moving rock on which we sit. And I can't resist putting as a last slide a paper of mine, which I'm not going to describe, which is in which I try to make sense of entropy in the same manner, and the title is the Arrow of Time Perspectival. If I understood this well enough to give you a convincing understanding of it, I would have put a picture. So science reveals a deep perspectival structure of reality. So that's my conclusion and my summary, my last slide. I just summarized the 4 points that I made. The first one, general. I claim that scientific intuition and scientific discovery, including in modern physics, contrary to what commonly said, are eminently driven by visual, by pictures. They're not restricted to that, but that's what the core of the story is. The second point is that I make is that science is a vision from a new perspective. It's a change is viewing the same reality from a larger, a closer, a different perspective, and therefore understanding it better. And the third point, which I made, I try to shortly to argue it, is that this contiguity between vision and science is actually deep. We're doing the same thing in vision and in science. We are detecting patterns in the experience which are stable enough to allow prediction, and we constantly test them and update them with the new data, update them when there are discrepancies. And finally, I was very fast, but I do believe that there is a deep perspectival structure in reality itself. And if we want to understand reality, we have to take into account strongly. We see reality from within, not from without. So there are only perspectival views of reality. And the idea that you see reality from the outside, which played a role in science, is not a good way for keep thinking reality, in my opinion. Piero della Francesca is quoted to say, nulla imag sine perspectiva, there's no image without perspective. I would say there's no science without image. Thank you. Thank you.
Thank you very much indeed, Carlo. That was amazing. I'm not sure that tomorrow morning I'll be able to remember all the detail of what you've told us, but I'll certainly remember the images and the imagery. Unfortunately, this is recorded. We'll all be able to watch you again next week and catch up on some of that detail. You paint word pictures as well. In your book, I really like the description that you give of time. time is like holding a snowflake in your hands. Gradually, as you study it, it melts between your fingers and vanishes. Immediately, we can see that happening. Thank you. Now, next week, Dr. Caroline Crawford, who's the public astronomer at the Institute of Astronomy here in Cambridge, will be lecturing on viewing the universe. So I hope to see you then. But finally, and again, Carlo Rovelli, thank you very much indeed.